All right, let's get started. Get my sign-in sheets passed around. I did want to mention real quick, most of you heard this in concrete design, but I'll go ahead, for those of you who are just joining us. So we have a homework 1 that's assigned in concrete design and a homework 1 that's assigned in steel design. The homework is assigned today. If you open up the syllabus, it will say it's due on Friday. I'm having it due the following Monday in here. There's 2 reasons why. When you all turn in this assignment, I'm going to give you the assignment on tension members, and it sort of makes sense to push that one back anyways, but 2, if you're in concrete and steel, that way you don't have a homework due on the same day. So this homework is due on the 27th, okay? So everybody's clear. So the concrete homework's due on Friday, the steel homework's due the following Monday. I'll pull that up here in a second to show you what's going on with that. Today, I want to continue the discussion on lateral loads, particularly focusing a good bit of my discussion on seismicity, and we'll briefly cover some of the gravity load stuff, just to make sure we're all on the same page. Everybody that's in here that, either just listened to this or already had it in concrete design, just to make sure we're all on the same page, and get into some load combo stuff. One other question I wanted to ask, or I guess bring up. So when we come back, we're using these. So are they coming in the mail? Everybody got them? So we haven't really used them this week, and that's fine, but come next week when we come back after our holiday, I'd make sure and start bringing it. I know it's clunky and I know it's big, but make sure and have it, because we'll start tabbing stuff and learning where various guides are in the spec and whatnot, so you definitely want to have it. In fact, before we actually get into design, I actually make it a point to just talk about the anatomy of the manual so that everybody understands. Okay. Let's go back a bit. So, just because I wanted to pull a picture of the dog again. So we have lateral loads that we've been talking about, and there's really 2 primary force effects that we have to deal with, and that's wind and seismicity. We don't design the entire building to hold the structure back. We only design a certain component of it, and like for instance, if we're talking about a car accident, we don't design the entire car to hold you back. We put a seat belt in the car to hold you back, a certain system. And so for buildings, we have really 2 primary classifications of systems, either a brace frame, where we're actually physically installing braces in a building to hold it up during a given lateral event, or a moment frame. Moment frames are just where we use more rigid connections and deeper sections along a given frame line to keep the building upright. Moment frames allow for much more open access. You don't have a big brace in the middle of the building, so the architect's happy and it makes the owner happy, and it sometimes is necessary given the ductility requirements of the structure, but they are a little bit more expensive. And I know that sometimes that seems counterintuitive because there's not a big brace in the middle of the building, so shouldn't the brace be more expensive than this? And the answer is no, just because of all the complex welding and stuff that needs to be done over and over again. Brace frames are a lot easier from a fabrication perspective. We talked about wind last time. That really dominated our discussion on Wednesday. We looked at the wind pressure distribution on buildings. As the building gets taller, the wind loads increase. We talked about wind pressures on buildings and where that equation comes from. It's just a retooled Bernoulli's equation expression. Got pressure on one side, velocity on the other. Treat wind as a fluid, throw the unit weight of air in there and throw some unit conversions, get a wind speed in miles per hour into a pressure in pounds per square foot, and there you go. And then we just throw a couple adjustment factors in there for various things like the exposure coefficient for the height, that's the big one, but then some others which are usually constants in most cases. We talked a lot about risk categories, which are going to come up again for seismicity. Again, risk category 1 falls down, it sucks, but it's usually not a big threat to human life. Risk category 3, you got a bunch of people in one building, or are buildings where the people inside have a limited ability to escape. And then risk category 4, where if that structure comes down, it's not just going to affect the lives of the people in the building, but it'll affect the lives of people in the community. So like hospitals, police and fire stations, etc. Like I said, the real big constant is the KZ value, and that example that we did last time was really sort of focused on making sure that everybody understood how to compute KZ. I mean, everything else was pretty straightforward. Just look up the wind speed, choose the appropriate constants, and you were good. And so, did anybody have any questions about example 1A? Okay. Let's talk about let's talk about seismicity. Before I do, just making sure I mentioned that I'd say the two primary other wind-related issues: internal pressure, and so where you can have positive and negative internal pressure in a building when wind hits it, and also the idea of the fact that there's all sorts of different load cases. The wind can hit this way, the wind can hit this way, etc. Okay, seismicity. All right. This one is a little different because with wind is kind of hitting buildings, like it could sort of hit all the time. I mean, you could have a windy day, a not windy day. It could, I mean, any one day could see, a series of wind loads. But seismic events are a little different. Seismic events, if you have a big seismic load on a building, it doesn't really happen all that often. It's not like, Los Angeles is seeing earthquakes every day. I mean, yeah, they get earthquakes, but it's not all the time. It's, these extreme events. In the world of structural engineering, there's a term called extreme events. And extreme events are just that, events that are somewhat rare and that don't happen throughout the day-to-day performance of a structure. And an earthquake is one of them. So if you were talking about, let's say we were designing a bridge. Let's say we were looking at the pier of a bridge. One extreme event would be an earthquake. Another extreme event might be a collision, like a boat or an ice collision into the pier. That's not something that happens all the time, but it can happen, right? So those are extreme events. And under extreme event design, our philosophy changes a little bit. In other words, we really don't care if we have to replace the entire structure once the extreme event is over. In other words, that building might be trash once the earthquake hits it, just as long as the people can get out alive, okay? So our philosophy changes a bit, and the way that we design structures changes a bit. When an earthquake hits a building, there's no earthquake monster pushing on the building. What you're doing is you're not putting a load on the building. You're taking the building and you're pushing it through an acceleration. So it's like being in your friend's car, your friend's driving, they hit the seat belt and you fling forward. And you fling forward because there's a sudden change in acceleration. Now, if you've ever been in like a vehicle accident, like a big one, a lot of times people who are in major vehicular accidents report that they're sore here and they have the sort of like the road rash type thing across their chest because of where the seatbelt was. But it's not like there was a seatbelt monster that just went like this. What happened was you went through a sudden change in acceleration, and what caused you to experience that injury was the sudden change in acceleration combined with your body's mass, your body's weight. That's where the force came from. And with earthquakes, it's the same way. The building experiences an acceleration, and the building itself is not very light, so force equals mass times acceleration. Pretty straightforward. One of the things, though, about earthquakes, though, is just the amount of force that can be generated in such a short period of time. I mean, you gotta understand, some of these design accelerations can be like 2 Gs. Imagine, I have a building, like a 30-story building, okay? It's like this. Here's the ground, here's the building. If I take that building and pick it up and hold it like this, that's 1 G, okay? That's the building under its own weight. Some of these events, they can see like 2-3 times, 2-3 G, 2.25 Gs. You have any idea how much force that is? I mean, a 30-story building, that's a lot of load, right? And if you recognize that, you have to come away with a realization. If you put a building through 2 Gs or something like that, I guarantee you something in that building is going to fail. Like, it's just going to happen. There's no way around it. And if you tried to design the building so that nothing would fail, it would be impossible. Instead, what we have to do is we have to sometimes be a little choosy about what fails. Let me ask you a question. Why do we have fuse boxes in houses? Why?
So it don't burn down.
Okay, talk me through that. So, what do you mean?
We can call it electrical engineer. We can call it firm.
All right, let's use our civil engineering.
Use it from shorten out pretty well.
Okay, so your house experiences a surge of electricity, right? So you have a house. That house is supplied power from the power company, right? Usually you would hope that the power company is supplying your electricity at a steady, controlled rate. Let's say there's a surge of electricity that hits your house, a bolt of lightning, whatever, right? You have a system in your house called a fuse panel, right? The idea is that it would trip before that surge of electricity hits your house, right? If that system wasn't there and that surge of electricity hits your house could burn down, right? Now let's talk about that from an engineering perspective. You have installed a system in your house that's purpose is to fail. And it fails before the house does, right? Okay, so we do the same thing in this instance in regards to an earthquake. So let me give you an example. Okay, so here's the earthquake, right? Earthquake hits the building, right? So the building is, sort of shaking, maybe something like this, like it's going like that. Okay. Now this is a cantilevered beam, right? Building sticking out of the ground, cantilevered beam. So if I have a building that's sticking out of the ground, cantilevered beam, where's the worst case forces? At the top story or on the ground story? Building's going like this. Where's the big forces inside the building? Up here or down here? It's down the bottom. And if you don't believe me, just do this. Hold the book like this. It takes a lot of effort in your hand to keep the book upright, right? Whereas if I put some here, my hand, it gets eased up a bit, right? So the big forces are actually here down below, right? This is where the building's seeing a lot of forces. Okay, so there's a couple ways. Let's say we were dealing with a moment frame. And I'm just going to, the system that I'm showing you is just one example of a numerous amount of systems, but I think it's one of the ones that's really easy to understand. So here's the building, okay? There's a couple ways that this building could fail. So it's going like this, okay? One of the ways that it could fail is that the columns could fail, okay? If the columns failed, that would be bad, okay? Because if the columns failed, the whole building is falling down. Okay, we have a name for that in structural engineering, and it's what's called a soft story collapse. In other words, you have one story of a building. Here's an example. So you have one story of a building where the columns failed before the whole building failed. And so, look, the building's fine, but those first story columns failed, and it's gone, right? So we certainly wouldn't want that to happen. Now keep in mind, this frame is very, very rigidly connected. So the beams and the columns and all that's all acting as one unit. So the columns could fail, but that would be really bad. The connections between the columns could fail, and that would be just as bad because it would pretty much mean the same thing. So if you're going to force failure inside the frame, you don't want it to be at the columns, you don't want it to be at the connections, so where would you want it to be? The beams, right? Because if the beams fail, yeah, it sucks, but it doesn't mean the whole building is coming down. So one of the ways that we do that, and again, this is just one of a number of sections, is we use what's called a reduced beam section. Let me see. Oh, maybe I can do this. Okay, so this is a reduced beam section. So you have this beam that's in a moment frame, and if you notice, one of the things that they did is they actually sort of cut material out of it. You'll see that? So what they did is they actually created a weak spot in the beam. Like you've got this beam and they cut material out of it to make the beam weak at that particular point. And they do that for a very specific reason. It's like if it's going to fail, I want it to fail there, right? Because again, if you have a frame, if the beams fail, yeah, it sucks, but it doesn't mean the whole building's coming down. And the thing about steel is an incredibly elastic and ductile material. So like, for instance, this is just an analysis showing all the forces in a beam under a cyclic load like an earthquake. And you can see that it can handle like quite a bit of stress before it starts to fail. Like back in World War II, when the cities in Europe were getting shelled, one of the things that they would do is they would build these cages out of steel inside their houses, and they would get inside the cage, and the steel would absorb all the energy from the blast, and they would survive. Steel is a very, very ductile material. If you look at its ability to withstand all of that energy, so it's a really optimal choice for earthquake design, just because of its ability to withstand all of that ductility. Okay, so let's talk a little bit about seismicity and where that comes from and how we go about this for design. So if we're in design mode, what we have to do is we basically have to figure out how we're going to design the structure that's going to hold these loads up. And so, like I said, there is no earthquake monster applying forces to the building, but there is the mass of the building, and the building is undergoing an acceleration. So force equals mass times acceleration. So when you're trying to determine, when you're trying to do seismic design, basically what you're trying to do is come up with equivalent loads. And those equivalent loads are basically going to be a function of the total weight of the building and what's called this seismic response coefficient. And that seismic response coefficient is really just a function of where the building is, the ground accelerations at that given location, and what's called the building's period of vibration. And we'll talk about that here in a second. And that'll basically determine the total weight of the building. So that you could sort of think of the weight as the mass of the building, and the seismic response coefficient as the G is the amount of that gets applied laterally for an earthquake, and that'll give you the total base shear. And then you just take that total base shear and distribute it to each frame as if it was a force, and then you like build a RISA model and design for those forces. Now, where do you get your ground accelerations? Well, it depends on where you're at in the country. Where you're at in the country can change the amount of earthquake forces that you have to design for. And to be honest, we're in Huntington, West Virginia. Our earthquake hazard levels are not very high, but depending upon where you are, they can jump up dramatically. Most people don't realize the presence of the New Madrid fault line along western Kentucky and western Tennessee. Their earthquake hazard levels are just as high as some of the regions that you would see out in California. So if you're out there, you have to consider seismic events. So it's actually not even that far away. So it's something a lot of people don't think about. Hawaii, Alaska, California, all located around the Ring of Fire, so they're definitely going to see some high seismic demand. And so it's definitely something you have to consider. It's also something that we can look up online as well. What we're going to do together, and this is pretty straightforward, we're going to determine this typical seismic response for what would a building be like here in West Virginia, and this or in Huntington. This is going to be really simple. It's just me using this website that I showed you. So we're going to go back to this website again. I've got the links in the notes. Instead of using the latitude and longitude here, I'm just going to enter the address. Now this links to Google Maps, so if you're using addresses, it's pretty easy. I can just say Marshall University. Oh, I think did it pop up? There we go. We'll say this is close enough. Okay. So wind, snow, tornado, seismic. Now, in order to do seismic, you actually need to know two things. You need to do the risk category of the structure. Okay, so the risk category, we'll say it's risk category 2, so that's just sort of a normal everyday structure, and the site class. Now, the site class is a function of the type of soil that you're constructing the building on, and that matters because the soil characteristics under the building, so if we're talking about this building, the soil characteristics under the building are going to affect how an earthquake gets transferred to the building. So in other words, the amount of accelerations that get applied to a structure in the event of an earthquake are going to change if you've got really loose clayey soil versus if you've got really like rocky, stiff soil. You know what I mean? It's going to change. Now the default is Class D or stiff soil, but that's just going to be a function of your geotechnical engineer and your structural engineer coming together and saying, okay, this is about what we need to do. So we'll just do Site Class D, and here's what you get. So first off, whenever you generate a seismic report, you get like a lot of data. Well, I mean a lot of stuff, like long transition periods and peak ground accelerations and all this stuff. Like, it's a lot of stuff. Really, what matters for a designer is this stuff right here. What you get, let me explain how this works. So the maps and the location where you're at in the United States comes from this. And so we have ground motions for short periods of acceleration and what are called long periods of acceleration, so depending upon your earthquake. We then modify that based on your soil conditions, and then we adjust that for what you need to use for design. And so it's not as simple as just here's your ground acceleration. It's a little more complicated than that. So we have these two values, a design spectral acceleration under short periods, and then a design acceleration under long periods. And I keep using these terms periods and periods of vibration, and I haven't really explained that very, very carefully. And I'm about to here in a second, don't worry. But basically the way it works is you develop these curves. It's like, as a function of the period, what is the acceleration that you need to use for design? So let's talk about that, and let's talk about what the period of vibration is. Okay, so you'll generate a curve that looks something like this. I just want to show you something, just so that you can be aware. We just generated a curve for Huntington. These are some typical curves. This is one from New York, and this is one from LA. So look at these accelerations, like 1.2 Gs, 1.4 Gs. This is some pretty hefty forces. But notice they're all a function of periods. Okay, so what's going on with the period? How many of you have ever played a guitar or a bass or some sort of stringed instrument? I'm just curious. See, I tried to play bass. It didn't really work out. It's hard. It takes a lot of left-hand strength, and I just didn't have it. All right, but has anybody have seen a guitar? Everybody's like just staring at me. You know when you go, right? Okay, all right. Now, if you've ever seen a guitar, and it's the one day I wish I had a guitar with me, and I don't, but there's something that's kind of worthy of mentioning about a guitar. Okay, so you have a guitar. Let's say you have your B string. Okay, now you can play that string a couple different ways. You can take that string and you can play it very, very lightly, or you can wail on the thing and it'll go, and it might sound a little rougher. Like the note might not come out as clean, but one of the things that you'll notice is that it's the same note. It's actually the same musical note. It might sound a little rougher, but dependent upon whether you play that note very softly or you wail on it, you're going to get the same note. Make sense? There's a reason for that. Okay? So the mechanics of playing a note work like this. Okay? So you have the string. Right? You take the string and so how do you play a guitar string? How does it work? So you take the string and you're basically sort of pushing it and then letting it go. And then the string goes, right? So you take that structure and you apply an initial displacement and then you let it go. And then you allow that structure to vibrate. So far so good? Okay. What it's doing is it's undergoing a mode of vibration. And specifically, it's undergoing a mode of free vibration. We call it free vibration because it's vibrating under the presence of no external load. In other words, if you have a guitar pick, once your guitar pick leaves that string is vibrating all on its own, right? Make sense? Okay. Now, here's the thing. Once structures are undergoing free vibration, it's a fundamental law of structural dynamics that under free vibration, all structures have an inherent natural frequency upon which they vibrate. It's why if you take a guitar string and play it lightly or wail on it, it's why it plays at the same note. Okay, because it's once your pick leaves the string, it's under free vibration. Does that make sense? Here's another thing about guitar strings. If I have a given guitar string and I want to change the note on that guitar string, how do I do that?
Change the length of it.
You change the length of it. What does that mean? Like, tell me what I do.
You press it down.
You press the string down on the fret. Okay? So you all took me for structural analysis, and you know that, for instance, the deflection of a beam is a function of how long it is. In other words, if I have a beam that all has the same loads, but I make it longer, it's going to deflect more. I've changed the structure by changing its length. When you have a guitar string and you press that string against the fret, the rest of the string now has a smaller length, so it becomes a different structure. So when you play that string, because it's a different structure, it vibrates at a different frequency, hence a different note. Does that make sense? So the way that you, so there's 2 points I want to get across with that. The way that you determine a natural frequency is a function of the properties of the structure. In other words, change the properties of the structure, you get a different frequency. The second point I want to get across is that once it's under vibration, under free vibration, it all vibrates the same. It's all the same frequency. That makes sense? Okay, so every structure, now I'm talking about guitar strings, but the same thing is true about buildings and bridges and everything. If an earthquake hits structure, okay, and the structure undergoes vibration, that structure is going to behave according to its own natural frequency, okay? And there's really 3 quantities that define how a structure behaves under vibratory loads. It's mass, so think if that guitar string was heavier, it wouldn't vibrate the same. It's stiffness, how strong it is, and then there's this thing called damping. Damping is actually really, really hard to characterize, but it's really easy to understand. If I take a guitar string, I set the guitar here on the table, and I play the string, it'll go bing, and then it'll slowly die out, right? The vibration will sort of peter out. That's what damping is, because there's a lot of friction developed inside the string, and it'll slowly die out. And so buildings have that as well. It's very, very hard to characterize. So much so that because, like, there's really a couple ways you could go about characterizing the frequency of a building. So what I'm talking about here is not just, so when I say the frequency, I've been using that term frequency. Frequency is essentially the number of vibrations per second, right? So 10 hertz versus 20 hertz versus 30 hertz, what have you. That's what I mean by frequency. The flip side of that would be the period of vibration. In other words, the vibration, sort of assume that it's a big like wave, like a sine wave. How long does it take to go through a complete cycle of vibration? That's the period. Okay, everybody with me on that? Now, remember that there are 2 primary systems that we use in structural engineering to resist lateral loads. We have braced frames and we have moment frames. Now, if you're looking at brace frames versus moment frames, they have different properties. They have different stiffnesses and different masses. So they have different frequencies. They don't behave the same way. They have different periods of vibrations. Braced frames tend to be a lot stiffer. They don't want to move as much. Moment frames tend to have a little bit more wiggle. They tend to play a bit. So as a result, we have different ways of computing frequencies. This equation in the spec is a really, really basic, straightforward way of approximating the period of vibration for a building. You want to try and determine the actual period of vibration for a building like this. It's really, really complicated and 3-dimensional. You better hike up your sleeves. That's a really complicated task. But under design mode, we need something that's kind of basic and straightforward. And so the spec provides us a nice little approximation. So the approximate period of vibration is a function of the height of the building and these coefficients. And these coefficients depend on whether or not you're looking at a brace frame or looking at a moment frame or so on and so forth. And for our purposes, we really just need to look at whether or not we're looking at a moment frame or a brace frame. Does that make sense? All right, does anybody have any questions on this? This is good stuff. All right. Now, once you determine the period of vibration of the building, there's a couple other parameters that go into that. But basically, the idea is, okay, I've got the period of vibration, and I've got my design acceleration. So based on the period of vibration, I can go here, look up, and okay, there's my acceleration. And the acceleration is primarily a function of how important the structure is. So we're going to develop different accelerations, whether or not it's risk category 1, risk category 4, what's the period of the structure, what's the location of the structure, and then how much yielding is tolerated. And how much yielding is tolerated is a function of the type of structure that we're looking at. And to be honest, I'm going to say that's a little bit involved to actually go from the period of vibration to the CS value. It's a little bit outside of what I want us to do in an undergraduate structural engineering course. If you took an earthquake engineering course or an advanced steel design course, we'd go through this in very, very significant detail. But we just don't have time for our purposes. I just want you to be aware of this. Now, what I do want you to know is once you get that acceleration, how do you distribute that throughout the building? It's really, really simple. Basically, you just use this equation here on the bottom. It looks a little nasty, but it really isn't. It's just a function of the weight of each floor, the height of the story, and then this distribution coefficient, and you'll see how that gets applied here in a second. Don't worry, we're going to walk through this in very, very explicit detail. I want to go back to that building that we were looking at before. I have, I guess you could call it a four-story building, or a building with 4 floors. I have the roof, and I have the 4-story, 3rd story, and 2nd story. Typically, when you're designing buildings, the roof weighs a little bit less than the stories, just because of the structure that you use. We have a commercial office building in Huntington, West Virginia, risk category 2, site D, and we're going to take the seismic response coefficient as equal to 0.1, which would be about typical, I think, or close to what you get around here. So, this is, I think you're going to find this is pretty straightforward. Okay. Okay. Oh, goodness. The pen is breaking up on me. Okay. We might have to divert to the board here in a second. All right. I'm curious. Can somebody tell me the total building weight for this building? What's the total weight?
$800 kip.
Say it again.
800 kip.
Everybody okay with that? So we'll say that weight is 800 kips. Okay. Now, the problem gave us the seismic response coefficient of 0.1. With the acceleration and with the site conditions, we could determine that, but it's a little bit involved. So, in most instances, for our purposes, I'll probably just give that to you. So, essentially, if I've got the total building weight here of 800 kips, and a response coefficient of 0.1. So that's like saying the building's going to undergo 0.1 G's of acceleration. So what that means is that our total base shear is going to be 800 kips times 0.1, which is 80 kips. So let me see if I can reproduce that here. In other words, so this building is going to see an equivalent seismic force of about 80 kips. So the big question is, I got 80 kips and I got 4 stories, the 2nd story, the 3rd story, and the 4th story, and the roof. How much force needs to go on each story in order to ensure that that's distributed appropriately? Now, before we do that, we kind of need to look at the approximate period of vibration. In other words, if I put this structure under free vibration, how much time does it take to undergo a complete cycle from beginning to end? Okay? Now, the expression that we use to do that, sorry. This is our means by which we compute the approximate period of vibration. So it's CT times HN raised to the X. And again, that's just an approximation in order to get a good enough value for government work for the vibration. So it's a function of three things. It's a function of the coefficients and the structural height. Now, for this building, we're dealing with a moment frame because there's no braces in the middle. It's all just open. So that means this is going to be 0.028 times whatever the height is raised to the 0.8. And so I use those numbers because this is a moment frame as opposed to a brace frame. Everybody okay with that? Now, for the height, well, the height depends on the structural height of the building. What is the height of this building? I'm asking you.
53.
53 feet, right? So we'll say 53. So somebody tell me what that comes out to be.
$0.671.
0.671. Do I have a second on that? Okay. Now just so you're aware, the units for this are in seconds. Okay? So, I'll put that up here just so I have a record on it. Oh, Lord. Okay. So the approximate period of vibration for the building is about 0.67 seconds. So in other words, if I put this building through an earthquake, it'll take about 0.67 seconds for it to go from here, and then vibrate, and then come back. So it's a pretty short period. Okay? Now, why that matters is because when we distribute our base shears are distributed using this, okay? And in order to distribute that, we need three things. We need the weight of each story, we need the height of each story, and then we need this distribution coefficient. So if our period is less than a second, what is the K value? Come on. 1, there we go. If it's greater than 2, or it's greater than 2.5 seconds, then K is 2. If it's somewhere in between, we linearly interpolate. Everybody comfortable with linear interpolation? Just, stretch it out. Let me say one thing. If there's like add, subtract, multiply, and divide, we need to be able to do that in here. The occasional square root and exponent, we need to be able to do that in here. Other than that, I'd say that, and some trig, the one skill you all really need for structural steel design is to be able to linearly interpolate. We will do that a lot in here. The tables, we'll have a value for 14 feet and a value for 15 feet. What's the value at 14.3 feet? We're going to have that a lot in here, so just make sure that you're comfortable with that. Okay. So, therefore, our K value is 1. Is everybody okay with that? Okay. So far, so good? So, let me show you how this works, okay? Because it's really simple. All right? Let's just take the 4th floor, and I think I'm going to have to skip using the monitor because that pen is really not liking me. I think I might have to next time go over there and maybe silently exchange pens. I didn't say that. Like, comment, subscribe. So, how heavy is the 4th floor? 200 kips. All right. What is the height of the 4th floor? In other words, from the ground to the fourth floor, what is that distance? Say it again. 41 feet. So therefore, tell me what the weight times the height raised to K is. Keep in mind K is 1. So I guess if you want, you can do it like that.
8,200.
8,200. Simple, right? Could you do that for every story? Okay. Let me pull something up. So I have this uploaded on Blackboard. It's that same spreadsheet that we looked at last time. So if you go to Design Aids, I have this spreadsheet. We looked at the one on the wind last time. So this is the one we looked at last time. This is the one we're going to look at today. So it's just, if you look at the bottom, just two different tabs. So if you look at the seismic force, so here I've got the total building weight, the seismic response coefficient, so it's a total base shear of 80 kips. The moment frame, this is what we got for our building period. It was 0.671 seconds. So because of that, our distribution coefficient was 1. Sound good? Now, I want to pay attention right now to these numbers, because that's what we just did, right? We got a story weight of 200 kips and a height of 41 feet, so that means that that term is 8,200, right? That was simple, right? Could I do that for every story? Like here's the one for the roof, here's the one for the third floor and the second floor? So far so good, right? Now, what I did is here I've got the sum of the weights, and here I've got the sum of these WH raised to the K's. The way this works is I need to compute this distribution factor, which is just this for a given floor divided by the sum for all the floors. So I did this for the fourth story. If you do it for the roof, the third story, and the second story, you get these. So sum all those up and you get like 21,650, right? So for the fourth floor, the distribution factor, so our distribution factor for the fourth story is just going to be essentially 8,200 divided by the sum of all these, the 2650 plus 8,200 plus 7,800 plus 3,000. And that comes out to be something like 0.379. Does that make sense? I'm hoping that math is pretty simple, right? So let me ask you this. Without doing any math, if I summed up all these, what should I get? 1, right? Because this is just a weighted percentage. So just take, so that's all this equation is. I know it looks nasty, but it's just, for a given story, it's that value divided by the sum. That's all it is. And so what this is saying is that story is going to see about 37.9% of 800. This story is going to see about 12.2% of 800. This story is going to see about 0.30 or 36% of 800. So if I'm doing the frame analysis, what do? So here's my building. That's the roof. That's the fourth story. That's the third story. That's the second story. So what would I do? I'd build this in RISA, and I'd put a lateral load here that's 9.79 kips. I'd put a load right here that's 30.3 kips, and etc. I gotta believe that's pretty straightforward. And does anybody have any questions about that? I don't like going from board to board, but my pen is being a little weird, so. Yes, sir.
I have kind of like not about this example, but a general question.
Yeah.
Would it be at all possible to like deal with seismic events by having the building with fixed supports and expansion supports on the other side to allow for like movement? That way the acceleration change doesn't like give you that internal stress.
Well, your beams would have to be real stretchy, right? You're saying allow the building to expand that way?
Yeah.
Well, your beams would be stretching a phenomenal amount, and what I'm saying is that steel beams just wouldn't stretch that amount. They would bend, but not stretch. Like if if you remember from structural analysis, we did an example in there. I don't know if y'all remember this, where we do a frame example, and we did the frame deflection. Remember, if you consider the flexural deformations, it deflected like 5 inches, but if you consider the axial, it was like 5.01. Y'all remember that? I don't remember the exact numbers, but structures are very, very stiff axially, but flexurally, not so much. So you're saying that you want the building to just sort of do that. In order for that to be the case, the beams would have to stretch. And I'm saying that they just won't stretch that much before they would snap. They'll bend, but not stretch. But there might be some ideas there. There are some, let me say this, there are some systems that use these like base supports that are made out of these like synthetic rubbers, and the idea is that they'll allow a little bit of movement. There are also, but again, we could talk about seismic resistance systems all day. Like, how many of you have heard of the Taipei 101 building in Taiwan, where they have that tuned mass damper in the building that counteracts, so when an earthquake hits it, the mass acts the other way. You know what I'm talking about? That's another way of handling this. But this is good stuff. Hopefully the math is simple. I just want to see if the concept's simple. Everybody has any questions? This is good stuff. Sound good? All right, so real quick, I want to show you what I've got on the homework. Now, let me show you one thing. I didn't have a chance to show you this. So this is the Blackboard page. I did want to show you that I've uploaded a good bit of material. If you go to course content, one of the things you will see is the homework assignment. And the homework assignment is just 2 problems. All it is I've given you a new commercial office building in Marion, Kentucky, and I just want you to do what I just did here with a risk category 2. We have a base wind speed of 115 miles per hour and a seismic response coefficient of 0.018. I just want you to determine the wind pressures and the effective seismic forces on each story. So basically akin to what we've been doing for the past week. And then for problem 2, I just want you to determine some of these wind speeds and locations using our hazard tools. So hopefully that's pretty straightforward. I did want to also mention, if you go into lecture notes, I've uploaded a lot more. I've uploaded the notes on the manual and on tension members, and this is enough to get us through exam 1. So just so you're aware, you can peruse that to your content. And also, if you look at the grade center, I've got a grade set up for the homework. Trying to think if there's anything else I desperately want to cover right now. I wanted to kind of cover the loads, but I think a lot of you either have already seen this or remember it from last year. So I'll do it really, really quickly when we come back on Wednesday, and then I'll discuss the manual. Any questions on the seismicity? The wind and seismic homework is due Monday the 27th, so we'll have class Wednesday. On Friday, be prepared to ask questions, so it'll be due the following Monday. Sound good? Well, we got a long weekend coming up, so you all have a wonderful break. We'll see you when you come back on Wednesday. No class on Monday. That's all we got.